Seng. And now where's the rest? Leave course already. Huh? Every got class. You know if they have class or not? Any maybe. Wait, another 2 minutes. In the meanwhile, do you have any question or not regarding yesterday lecture? Yesterday lecture. You try and prove the theorem. Yeah. Yeah. Okay. Sure. Yes. We will address this question today. Later, I will address this. Other than this, any other question or not? Can Brian help remind them the class here? Okay, I think we should start now. So, because next week there will be 2 holidays, and exactly it's our class meeting day. I think we should at least replace 1 day for next week, so that our assignment won't get delayed too much. So I plan to do Monday because you guys can't do 10 to 12, so we do 12 to 2. Is that okay? 12 to 2. Yeah. Wait, I thought yesterday we decided 10 to 10. What's wrong with what's wrong with, what's your schedule? What happened? 1 to 3. Huh? What place is that? MPU. Either you go half there, half here, or you watch recording, can or not? Can. Okay. Okay, sure. Because your schedule is quite different from others, right? Okay, I can excuse you if you cannot. What else we want to say? So I put out my assessment, right? At least I put 10 weekly assignment. It's because I got feedback from my previous batch of students because they feel that it's better to do it weekly so that they know what to use each week for the assignment. So that's why I make it weekly. So in return, you should expect a little bit shorter assignment than the usual long assignment. And yeah, so I'm pretty serious in this Pure Max academic, right? I'm pretty serious. Why do I say this? So I want you to have a right concept about mathematics here, right? Although your degree is maths and applied maths, right? So really, mathematics split into three branches at least. Right, first is pure, second is applied, and third is something like statistic. Okay, so these three fields are really different flavor. They are really different flavor. Okay, so for example, what kind of subject fell into this three category? So for example, in pure, you will see like analysis, right, algebra, or even this topology, geometry. Right? But pure for applied, for example, what kind of topic you could have? For example, combinatorics, uh, dynamical system could be quite applied. Um, what else? I would say maybe PDE, ODE can stand between here because okay, I will explain later. What's meaning by standing between here? And then statistic, what? Statistic, of course, statistic is here. Maybe financial maths is here as well. Or other econometric, what else like that. All these what differentiate these three categories is the level of rigorosity they use. Okay, do you just calculate apply formula, or you want to ask where this formula from? The moment you ask where this formula from, why this formula is true, they all have to go back to pure. Okay, makes sense or not? So I guess here the lectures are quite different in flavor, so you need to like see what kind of flavor they are trying to display to you. Okay, but for me, at least for me, I will just stay here. Okay, I'm trained in pure maths, so I do pure maths. But it doesn't mean that I cannot do calculation. I can do as well. So this is what I stress to Peter. The student here, okay, what's your degree? Anyone know what's your degree? You're gonna get after you graduate? Bachelor of what? Bachelor of what? I don't think so. Bachelor of what? I sit in the open day. The whole day I explain to people what's the degree here. Bachelor of what? You don't know? Bonus? You got honors there, but Bachelor of what? Bachelor of Mathematics and Applied Maths. And you see and so for this thing to be true, both of them have to exist. So that's why you are forced to study pure maths and statistics together. Okay, these are your core. You cannot throw one. You need to study analysis, abstract algebra, and then statistics together. So these are different flavor. You cannot say, wow, statistics very easy, that one very hard. No, they are different level. It's different, okay? You need to tell your friend, tell your student, okay? I think student council have to play a big role here. Things, their first meeting for orientation is useless. Please have to educate them, educate them. These are different level, okay? You cannot compare. Cannot. Okay, and then so these are different levels. So what? Okay, so what? So you should expect different things from different category. Okay, you should expect different things from different category. Yeah, right. Like the other day, trying to persuade my class, one of the good student, to join Pure Max. Of course, I failed, but I was quite happy. You know why am I happy or not? I told her, your result actually improved quite a lot because I taught them for 2 semesters from calculus 2 to abstract algebra 1. And I can see her really like grasps the knowledge and logic just by improving in logic. She say, what she say? She say, yes, sir. I was not good in logic before. Thanks for your class. So you need to learn something in this pure maths. It's not just about hard, abstract concept. Why people can get it, you cannot get it? You know? You know about, can you think about this question? So in my pure maths class, right, I try to be really concrete. Okay, I bring the abstract idea down to the earth for you to see. Maybe you cannot see this in the other lecture class. That's fine. But you have to see it in my class. And I hope you will bring this to your fellow friends or other people. Okay, so that pure maths actually is not that haunting. You can choose not to do pure maths, but please don't avoid it. You get what I mean? Your choice is okay. It's okay. You want to go finance because maybe you want to earn money, or maybe you have different path, is fine. But you see, you need to explain why you come here and take this degree. If you just want to be statistician, why come here? There's no like torture yourself, right? With pure maths. Just go Utah, just call other places, you know. Yeah, so you need to tell people what's about maths degree in Xiamen University. What you can get out of here. Okay. So maybe you ask one question, hey, why you provide so many branch since you are mostly in pure maths? Why you provide so many branch? Right? Because we want to produce different branches of people with pure maths of logic thinking. You know, this is different, huh? You get me? A pure statistician without maths degree and a statistician with maths degree is different. They think differently. They think differently about a problem. For example, in algebra, you learn about structure. So when you look at the data, you won't just see number. Maybe you see some kind of structure governing this data. You get what I say? This is what we want you to get on, right? Of course, it's hard. You need to sacrifice. That's all. Okay, things doesn't come cheap. Okay, please educate the student here, and then show them what's the real face of a pure maths. Okay, does it make sense? Make sense or not? Okay, so yeah. Okay, if that makes sense, then we will proceed to the unsolved problem yesterday. So one unsolved problem yesterday is I haven't defined what is index set. Why I don't bother to define at first, because really it's just a set. Okay, it's just a set that I want to use it to label something. That's all. So there's nothing special about the set. I just use some set to label another set. So it is called index set. But if we want to try to be more rigorous, we can follow this Moncrief's textbook here. So first, you start with non-empty collection of set, and then you define a function. Okay. So this function is called an indexing function. From this collection of set, okay, from where? Let me see. Yeah. So indexing function for this collection of set is a function. Okay, is a function. Is a surjective function. Okay, surjective function from where to where? From some set we call I, okay, to A. And then this I is called the index set. So meaning I label everything in A using something in I. Okay, this domain set we call it index set. That's all. So extra information here is this labeling, surjective function. Okay, so meaning everything in my collection of set, right? I can attach some label to it. Okay, so this collection with the index we call index family of set. Okay, because you start with a family of set and then you index it. That's all. So yesterday come out with a question: can I index using uncountable thing or not? Can anything you can. Okay, anything you can. So if I can do that, so what happened to my proof? Okay, so let's go back. What happened to my proof here? So we have proofs involving families, right? Actually, I posted out the lecture note. Hopefully, you have had a chance to see it before coming to the lecture. Let's see what's the this proof here. Okay, this proposition. So the part 6 here involve family of index set. Okay, but the claim here is you don't really need to know about this I to prove this statement here. Why? Why? Because this is due to the definition of union and intersection. What's the definition of union? You still remember? Union of family. Yeah, sorry, I think there's a typo. I haven't fixed in my notes. So I think I need to update it. So by the way, if you found any typo, please let me know and then I will fix it. So you see, union of AI means what? You take all the elements in sum of the AI. So when you choose some set here, there's no relation between whether you can order that set or not. You just that exists. Can you find one or not? Okay. So the proof here. Okay, so let's go down here. So let's go down to the proof here. So let's say we want to prove this this equality here. Okay, A intersect family union of BI. Okay, you get union of a family of intersection. So of course you need to do it two ways, right? Subset inclusion, but we will just use if and only if. Then you can go top to bottom and then go from bottom to top again. So let's go one way. If X is in this intersection, what does it mean? Meaning X is in A and X is in the union, right? And this is just intersection definition. If X is in the union means what? X is in BI or some BI. Here, I don't care whether this capital I is uncountable, finite, or what, right? There's no issue here. Then you just use a predicate logic that move your bracket around. If you like to be rigorous or pedantic, you can use the, is it called De Morgan? Wait, not De Morgan. I think it's distribute T, N and all. Okay. And you can turn it into a union of intersection. Okay. Make sense? Does it make sense? Any question about this? For intersection of family index of set, then you need to take for every I instead of for some I. Right? So this is the difference. But I don't really care how many things inside. So it won't be an issue here. And I don't use the inductive proof here. I just prove it at once. Yeah. Sorry, what? Huh? Yeah. Yeah, any question about this exact set? Yeah. Okay. So I'm not sure how many students will formally enroll in this class in the end because it's still changing right this week. Um, this Sunday is the last due date, is it? Or there are more times for you guys? Don't know. I think this week is the last. Yeah. Okay. So maybe will fluctuate a bit. But yeah, I hope for those who are serious for this course, try to be reached on time so that you don't miss anything. Right. Okay. Yeah. Yeah, I don't want to repeat again, but class representative, please help and you are not police lah, but you just act like how to say how to say reminder. Yeah, remind your friend like your friend and your friend you also will ask do you want to come to eat or not? Right? Do you want to come out or not? It's like that lah. It's not like wait you must come out now huh? Like that, you know. So yeah, yeah. So for those who are just arriving, one important announcement about replacement class is I will be trying to book a room for next Monday. What time already? 12 to 2. 12 to 2. Okay. Yeah. Once I confirm, I will let you know again. So far, only one cannot make it, and you can do recording if you like, or you can skip your lecture. But don't say I asked you to skip. Okay. Sure. So have we done settle yesterday problem already? Settled it. Yeah, so I didn't provide all proof because most of the proof reading a proposition is the similar cases, so you should try and write it down. If you have problems, doing it, what should you do? If you have problem doing it, what should you do? Ask me. Yes, please ask me. Don't go WeChat, scold me. Okay. Okay. So yesterday we stopped at this definition. Let's recall the definition of order set, order pair. Sorry. Okay. Have anyone tried out the proof or not? Anyone try out? Go try. Some of you try. Okay. Let's see. So this is our definition of order pairs. So order pair is a set. Okay, because we start with set theory, so we're trying to use set theory to build up this order pair. And what's this set? This set, to talk about set, what we need to do? We need to speak about the membership of the set. So what is in there? So in this set, there are two sets. Okay. Set contain X. Second set contain S and T. Okay. So you might think, wait, why you do this? Huh? So let's see why we do this. So one thing we want this order pairs to hold is, let's say two tuples is the same. Okay, these two order pairs are the same. We want that this is only true when they are true component wise. Okay, so meaning S1 equals to S2 and T1 equals to T2. Let's see whether this definition do the job or not. Okay, so let's prove it. Okay, so let's start from x1 t1 equals to x2 t2. Okay, so what does this mean? By definition, this is what? This is a equality among two sets. Let's see. If this two set is the same, right? What do you expect? What's the definition of equality of two sets? Yes, the element have to be the same. Okay. So you see, the set containing x1, right? Can it be equal to the set containing x2 or not? Maybe can. Can x1, the set x containing x1 equal to the set containing x2 and t2 or not? Cannot, right? Because that set of two things. So if these two gonna be equal, means what? The set containing x1 must be equal to the set containing x2. Right? Make sense? Okay, let me add something. Because x1 cannot be equal to x2, comma t2. Why? Because x1 equals to s2, then t2 equals to who? But 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 we don't list the same thing twice. We don't list same thing twice here. We don't list same thing twice here. We assume s1 not equal. Wait, let me think. Let me think. Am I correct or not? I think you bring out a problem here. So should I bet s2 equals to not equal to x2 or not? Wait, let me think. Okay, I know your problem. It's not a problem actually. Okay, it's not a problem. Okay, I know your problem. Okay. Okay. Let's write down this argument in full. Okay, so that we don't have any confusion. We're trying to be really concrete. Okay, so let me reduce this. Okay, so okay, let's revert. Okay, so we want to see whether x1 equals to the set containing x2 or x1 equals to s2 comma t2. Okay. My claim is the set containing x1 cannot equals to the set containing x2. Okay. The proof is the proof is okay. So the proof is if x1 equals to s2 and s2 equals to t2, then s2 is equals to t2 as well. Okay, so what's this problem? What is this problem? Any problem here? Any contradiction here? No contradiction. You know why there's no contradiction? Okay, so this will lead to a case, right? Okay, this will lead to a case where, let me see. So let me see. So let me try. I want to claim that this will lead to a case that x2 equals to t2 and then x1 equals to t1. This is the only case when it happens. Let me think how to write it down. So I think we break into cases. Let's break into two cases. Okay. Let's split into two cases. So let me think, is it enough to do that? So think. Okay. So suppose one case, so either x1 equals to T1, or sorry, let me see. Let's set this up. See how should I set this up? How many possibilities for this two to be equal? How many? Two possibility. What kind of possibility you have? Two possibility. X1 equals to T1, or S2 equal, sorry, X1 equals to, not equals to T1. Like this. Does it make sense? Sure. Of course. Okay. Okay, of course. Okay. Okay, let's see. So we should proceed with which one first? So our goal is what? Want to show that equals to, right? So here, this one is by assumption. Okay. So what should we do? What should we do? So what? So you see, by assumption, we know these two sets are the same. If we're gonna, yeah, sorry. Yeah, so this, so okay. So let me move this one to the left, and then move this one to the right, so that it follows the reading. When if x1 equals to t1, what happens? Actually, this set collapses, right? Huh? Collapse to what? To the set. And then it collapse again. And then, sorry, everything equals one? Yeah. That's what we want to get. But I want to like get it step by step. So, so we got until this stage here, right? But you see, on the left hand side is a set containing two things. On the right hand side is a set containing one thing. That means these two have to be the same, correct? Okay, if these two have to be the same, meaning what? They have to contain the same element. So if they contain the same element, then T2 cannot be different. Okay. Okay, now this one makes sense. So then suppose x2, sorry, s1 not equal to t1. Okay, suppose this case. Okay, we do the same thing. So let's do this same thing. Let's do this the same thing. So these two equal. So how we deduce that x1 equals to x2 and t1 equals to t2? So we will use the argument we had just now, right? Because the problem just now is we will get to the degenerate case. But even the degenerate case will give us the right answer. Okay, so we use the argument just now, say that the one element set must be equal to the one element set. Okay, otherwise you will go back to the degenerate case. Make sense? Yeah. Okay, this is more complete. But in usual textbook, they will just let it go. You need to feel it yourself. Okay. Does it make sense? Anyone? Oh, okay. Okay. Yeah. So I think the other direction should be easier, right? The other direction is easier. So once you have x1, x2 equal, t1, t2 equal, then obviously the two set equals. Okay, so the other direction is easier. So you see, this extra s here is to keep track. Sorry. So this extra x here actually try to keep track where this t is relative from x. So there's no information loss here because you want to order them, right? So this is trying to preserve the order just using set. Okay, that's why you can build a computer just using binary. Okay, does it make sense? Okay. So I mean, yesterday I mentioned a point that this proposition is a defining relation for the ordered pairs. Actually, we don't care how you define this ordered pairs, but what your definition need to do is this defining relation. You need to make sure that your definition do this job. Whenever two tuples are the same, okay, they have to be the same component wise. Okay, you cannot change the order. That's why this is called order. Does it make sense? Okay. Okay. So so an exercise. So exercise here. Try a define n tuples. Okay. Try and do this exercise. Try and define n tuples such that it has this defining relation, similar defining relation. And then prove that it works. Again, like what we did just now. Yeah, a very key part in pure maths is whether you can generalize something in a finite sense to infinite sense. Okay. Okay. Yeah, try to do this. So, all right, continue. So, definition. So next, we will define Cartesian product between two sets. Cartesian product between two sets, say x cross t of two sets, s and t. So what are these? Okay, so we're gonna collect all the pairs. T, okay, with S in S. So what does this mean? This means a set that containing all the pairs, such that S is in S, T is in T. Okay, so this is a Cartesian. So I think you met these before. Can you give me an example? It's calculus R2. Okay, R2. So you have seen if you have seen Rn, so try and define again. Okay, addition product for n set. Okay. So these are order n pairs. Order n tuples. Okay. So why we are looking at these things? So basically, we try to define functions using set. And maybe this is the first time you hear this, but it is not too short because it is related to the graph. But it's function as a set here. So now we will define f, okay, as a set. Okay, now function is a set. Set of what? Set of ordered pairs. Okay. So maths is like this. We will introduce definition and then later we'll use it. So you should expect what's the next thing. The next thing comes from the thing previously defined. So I just defined ordered set. So now I'm going to use it. If F is a set of ordered pairs from ST, okay, not random ordered pairs. with a property. I think you can guess already that for every S in S, okay, there exists a unity such that the order pair ST is in my F. Then we say that F is a function or map, okay, from S to T. Then we will write what? The thing you usually say. F is a map from S to T. Does this ring a bell to you? What's the function to you before? I give you an input. You can only give me one output. You cannot give me more than one output. Otherwise, I confuse. Where should I go? Okay. So for every S, you have a unique T in T. So S, the set S and T here, S will serve as a domain, T will serve as a codomain. Every S you should have only one T. This is function. Okay, so maybe I will remind you recall what's our function before, so that you will make more sense. So what's the function to us before? So a function from S to T, okay, is a unique assignment. Okay, it's an assignment of an element Fs. Okay, in T. So this S is small s to every element S in S. Okay. So I give you one input, okay, you give me only one output. Unique assignment. So this uniqueness here, we translate to a uniqueness in the set. And then some more terminology so that we can use later. Then Fs is called what? It's called the image. S, okay, under F, okay, under the map F, specific map. And on the other hand, S is called a pre-image. It's a pure image of S. Also, what are these two sets here? Just now I secretly used it already. So S is called the domain and the place you map out of, and place you landed in is called the codomain of F. Okay. Yeah. So please don't confuse codomain with range. Range is everything that can be met by F, but codomain is where the range lands in. Okay, so for example, actually you are very well equipped with this example, just that you maybe never see this in this form before. So for example, right, this graph here, say fx equal to x squared. Okay. So the point that satisfies fx equal to x squared, right? These are all ordered pairs. These are all ordered pairs. So I can write this f as ordered pairs f and x squared, such that x is in R. And this corresponds to what? This corresponds to a function. That's why we will label the function sending x to x squared beside this curve here. And then what's this ordered pairs? These are precisely the parameterization of the curve. Okay, yeah. Does it make sense? Try to tie everything together. This is how we do pure maths. Because in different language, right, we might have different result, and then maybe that result can apply, and then will help you solve problems, maybe in analysis, in algebra. So different theorems in different places. It's easier to prove, and then you can apply it in different field. Okay, that's how we connect different field in pure maths. Okay. All right. So this is one of the example about the equivalence between these two definitions. So let's finish up the example here, and then maybe we will take a break. Oh, let's see. Let's see first. Okay. So yeah. So this is the equivalence between these two. So you can try and prove. Okay, try and prove. So exercise. So exercise. Exercise. Prove equivalence. Equivalent definitions of function. Okay. So if I give you such a set of order pair, can you define a function or not? That give this unique assignment. Okay. Or I give you a unique assignment. Can you produce me a set of order pairs or not? Okay, so this is depicted by this example here. Try and write out a general statement. I think I will do this as well. I'll provide this, but you try and do it first. Okay. Okay. All right. So there's another example. I want you to see what's wrong with the mic. Hello. Okay, let's leave with it first. So there's another example. So let's consider a function, okay, from empty set to t. Does there exist this kind of function where t is not empty? You think this exists? Yeah, talk to your friends beside you, or in front of you, behind you, near to you. Whether this exists or not. Any idea? Any try? No. No, you think no. Most of you think no. Is it a function? What function is that? Nothing function. Okay, let's see what thing is this. What thing is this? So if this is a function, right? So we see function as a set. So meaning this is a subset of P cross T. What is P cross T? P cross T is T. How do you know? How do you know? Yeah, P. Why is it empty? I don't think you can just say like that. I mean, okay, so what's the definition here? So S is in phi cross T means what? X has to be in phi and X has to be in T. But this thing is false, right? So false and always false. So nothing will satisfy. That's why this is an empty set. Can you find a subset of an empty set? Empty set. Oh. So you can take F to be we call it a empty function. There's only one such function as this. What? Which one? Yeah, correct, right? Cartesian product. Okay, here. Yeah, ST such that S is in S, T is in T. Uh, sure. That's sure. Fine. Well, below. I just put comma, right? Comma, comma also n, right? Comma is also n, right? Comma is also n. So, okay. This is just some notation. Yeah, some notation. Yeah. You cannot say cannot end, right? You cannot say when I write st, right? Hey, this one don't need follow lah. This one follow only. Cannot like that. Correct? You know what I mean? So actually, there's an implicit n here. Implicit n here. But this is different from intersection, right? Because we include both things as our element, not just one thing. And then we consider n with different element, not just ss is st. They could be different. S and t could be different. We take all of them. Okay, this is the difference between intersection. Intersection is ss, right? Here is st. Could be ss or st. Does it make sense? Somewhat similar, but the thing the variable considered different. Yeah. Okay, so f is the empty function. So there's only one function can do this job. Actually, maybe I give you some extra stuff here. So actually, this is what we call this phi. Phi have this property that we call that it is the initial object in the category of set. Okay, it's the initial object, meaning there's only one map can map out from the set. Okay, so it's the initial object. There's only one map can map out this object. Okay, hopefully one day there'll be a course on category here. Okay, yeah, so if you don't get this line, it's fine, but what I want you to get is there's only one map coming from phi to anything else, which is the empty. You can try. See if you can formulate this function in this assignment way or not. You can try. Since these two definitions are equivalent, right? You should be able to formulate it in the other definition. Okay, try and do it. Should we take a break now? Should we take a break? Let's take a break until 12:05.
这个可以，别人都为什么我不用这么复现？举的赛格可以从零变是一样的，就是从1、2、1、2、3过来，但是这个是一样的。
这个还没有写完是吗？
写完了就是这个的话，就是从1月，这是一，也是一个，然后1、2、3，然后这个也是1、2、3，这个的话也一样，这是1、2、1、2、3、1、2、3、1、2、3，那就他们两个表示就一样。
哦，我知道你讲什么是。
就不知道怎么翻。
对对，我懂。哎，你照一下发给我，我再想一下。Let's take some attendance. 周一分资源 Do you know who are the who are them like the two I mentioned because they are from your batch. Still in China. Visa, huh? Visa problem. Okay. Brian, okay. Gary, okay. Jian Xiang, yeah. Ju Juje, Juje, huh? Okay. Okay. 至于金波定宇、子谦、三叶、嘉怡，会嘉怡的吗？OK。 So let's go on first. Okay, let's go on. All right, so just now I mentioned about range, right? So let's define what's range. So let R be a subset of X and a function from S to T. So because due to the equivalence, you can think of it as a set, as an ordered set of ordered pairs, or you can think of it as a unique assignment. Okay, you should be able to sort between these two freely. And the image FR of a set R under F is the set that can write as F capital R equals to FR where R is in R. Okay. So if R is just the domain itself, then this set is what we call the range. Okay. Why we introduce like seemingly quite troublesome definition, we consider subset of domain, because sometimes we just want to see portion of our domain where it maps by this F. I don't want to look at the whole thing. I just want to look at something inside my domain. Okay, but with this definition, we can generalize it to look at the whole domain. When I look at the whole domain, where's the image of the whole domain? This is simply the range. If range, okay, later I will. So, should I say first? I want to be a spoiler. If the range equal to the core domain means what? The function is surjective. Okay. Yeah. Okay. I will recall what's surjective again. So, example here. Okay. Why I put this example? Okay. Never mind. So, for example, okay. Let's say, for example, the identity function from X to X. So, what's the image of X here? It's just S, right? Sense, can follow? Okay. Definition. Let again Q a subset of T and function S to T. Okay, so now we look at a subset of core domain now. Okay, so what am I trying to do? I was trying to define pre-image, something before the image. So what's the thing before the image? This is what we call the F inverse. F inverse. Okay, not inverse of F, F inverse of Q. Okay, so this is a set. You should have seen this in abstract algebra. If not, I record it here. So what's this set? F inverse of Q is what? Is the thing inside your domain. So what are those things inside your domain that you want to take? Such that F of S is in Q. So let me draw a picture to you. So really, these are quite geometric. I mean, topology, if you like. So let's think of S and T like this. S and T. Okay. So let's look at some Q. Okay, Q maybe is a subset of T. Right. So what is F inverse Q here? So F is inverse Q is something here, let's say. And inside here has something we call S. Under the map F, this Fs should lie inside Q. So the whole thing is F inverse of Q should map to Q. Yes. Okay. Yeah. So picture is really useful when you look at this definition set or what. Okay. Don't forget your Venn diagram stuff. You can use it here. So one very important remark here. Please don't confuse this F inverse Q with, don't confuse the pre-image or the inverse image set with the inverse of F. Okay, although we use the same notation here, similar notation. Okay. Okay. So there are a few propositions we get here. Okay. How these inverse function interact with intersection and union. Okay, so let's see what kind of interaction we get. So let's given a function. Okay. Don't specify the domain and codomain here. There should be a sensible domain and codomain for them to work. But what we are getting here is f of S union T. Okay, f of the union of two set is just Fs union Ft. Okay, so to prove this, what do you need to do? Subset inclusion. Okay, and then use the definition of image, and then use the definition of union. Okay, so you should do it. Okay, second, how about intersection? Intersection, we only can get one direction. Okay, f of an intersection is just a subset of Fs intercept Ft. So since the other direction didn't work, right, you should be able to come up with a counter example. Okay. Can you come up with a counter example why the other direction work on the spot? Can you come up on the spot why the other direction won't work? Sentia, a joint. A disjoint, you mean? Okay, a joint is very high level word in category theory. Okay, disjoint. When S and T is disjoint, when S and T is disjoint means what? This thing is a F of empty set, right? F of empty set is what? You sure? F, can F map empty set or not? What's that? F of, wait, let me think. Can, just now we did it, right? No. Just now is the empty function. What's F empty set? There's nothing here. So what is F empty set? What should F empty set be? Sure. Should we go back to definition? Okay, let's go back to definition. Good. Testing my definition. Okay, let's bring this down. Okay, good. So okay, surely phi is a subset of any domain. So it's equals to phi of, come back. Okay, so wait. So here, so f of phi is equal to what? Is fr such that r is in phi, but nothing is in phi. So again, should be empty cell. So so this side is an empty set. So you need to produce. So you need to make sure that this intersection is non-empty, right? Okay, can you do that? Which example? Y equals to y equals s of fx equal to x squared. Okay, and then
S is
S is closed interval or open close. So okay. Or 1 to 2 or interval. You want interval or element? Interval, right? Okay, S is 0 to 2. Huh? Let's say open. Huh? -2 to 0. Okay, so what is fx here? Is again 0 to 2. Okay, how about ft? Sorry. Yeah, squared it. Okay, 0 to 4. How about -2 to 0? What's the image? Same, huh? 0 to 4. Okay, but S-intercept T is okay, it works. Okay. I was trying to use the diagram to do it. It's like you have these two intersections, right? But inside this intersection, you can have something that maps from not the intersection. Sense. So exactly the same. You are looking for some non-injective function. Sorry, yeah, right. Non-injective. Sorry. Yeah. Makes sense, huh? Okay, so here is the counter example for the other direction, the other subset included. This kind of counter example is very important. This is where I can test your concept. Okay, you should be able to construct this simple example. Okay. All right. Next. So F inverse of a union of set is equals to F inverse of X union F inverse of T. Okay, so it is equal. Surprisingly, inverse image work quite well with union and intersection. It also equals to the intersection of inverse of X and inverse of T. Okay. How about complement? Okay, let's see how inverse act with complement. So if you take the complement of an inverse image, is the inverse image of the complement of X. Okay, so the complement move in. And last one is A is a subset of F inverse F. So if you have an A, map it across, look at the pre-image again, and this thing is usually larger than A. Try and find counterexample for the other direction. Okay, so for 1 up to 4, right? So you see it works for two sets. So you can generalize this actually to family of set. Then you can generalize it to family of set. Okay, try and prove them. Okay, so these are very standard exercise to try and prove them. Okay. Should we prove any of these or not? Or yeah, okay. You guys have any idea? Skip it. Skip it. Okay. Yeah. So try if you can come up with a counterexample for the other direction. For number 6. Okay. Next, we will talk about injective and surjective. Okay. So what is injective? Actually, there are few equivalent definitions for injectivity, but we will take this one. So a function is injective, or sometimes you will heard one-to-one. If fs1 equals fs2 implies s1 equals to s2. Okay, so in this case, this function we will call it an injection. Okay, f is called an injection. Okay. Sometimes, right, we will write like this. So instead of writing injection, I will write f from s, a hook arrow to t. Yeah, a hook arrow. Injection. Inject into t. So it's like, so why I put hook? So you are thinking as this s, right, is sitting inside t. Okay. So how do you do injection? You need to like inject into, like, for example, s to t. You need to be able to sit inside t. 1-to-1. There's a 1-to-1 correspondence between this, not 1-to-1 correspondence, but 1-to-1 relationship between x and the subset of t. Okay. Let's hook arrow here. Okay. Next one, surjective. How about surjective? Surjective is quite straightforward. Just now I said that the function is surjective if the range and the codomain is the same, right? So meaning what? Meaning what? Meaning a function is onto if for every element in the codomain, what can I do? It is the image, okay, of some elements in X. Okay, so that means what? That is for every t in T, okay, there exists some X in S such that fx equals to t. Okay. So everything you go to a codomain, it is coming from someone in the domain. So in this case, we will call this f what? Just now we call injection for injectivity, right? So here we call it surjection. So the notation for the surjection is we put a double head arrow. 正中靶心, okay, hit everything. Okay. So a very easy proposition is if f is a map from S to T, which is surjective, then fs equals to T. Okay, this one almost follows from definition. I think there's just two lines. So in this case, you will see the book maybe write trivial. Okay, but try and write it out. Right. Exercise. Because this short exercise is very good for you to check whether you know the definition or not, how you use the definition. Because in future, the proof will get longer and longer and longer and longer and longer. And then they will hide a lot of detail inside it. So it's very crucial that you can expand this detail. Okay, try and write down. A function, f, we will call it bijective. Okay, bi mean two things. What are the two things here? So if it is both injective and surjective. So in this case here, we will call this map a bijection. Okay, I think you heard a lot of bijection. Or sometimes you will see you will call this and one-to-one correspondent. Not just one-to-one, but one-to-one correspondent. So you can go back and forth. You can go back one-to-one correspondent. So maybe the notation will become a hook plus a double head arrow. But we seldom use this, but it could happen. Okay, so what next? Okay, next let's define composition first. Okay, let's define. Okay, since we're already at this stage, right? Let me see. Since already at this stage, maybe just continue defining invertibility first. So a function is invertible if what? There is another function, okay, going the other way, such that what? Such that GF, okay, all right. So I think we really skip something here. So GF is the identity on X, and FG is the identity on T. Okay, so what's this comma, this circle here? So if you use latex, this one is a slash CIRC circle. Okay, so what's this circle here? So how do we define this circle here? So this is none the other function which we call the composite function. Okay. So let's say we have two functions, not random two functions. You can see that these two functions are in sequence. So I have first mapping from S to T, and then second one T to U. And then we want to define the composite function GF. GF from S to U. Okay. To be what? How do we define this composite function? So to define a function, right, you just tell me where my input gets sent to. What can I do? I can send my input through F first, right? And then it's something in T. Then I can use G to send something in T to U. Okay, so this is just G on Fs. Okay. Yeah. So okay, another notation here. Identity on X, identity on T. Does everyone comfortable with this notation? It's an identity function on X, so S to S, and then identity on T is an identity function from T to T. Okay. Check whether you have the right domain and codomain or not, because F is going from S to T, and then G is going from T to S. So you start with S and add S. Okay, similarly for the other case. So one okay, before we tying this bijection and invertibility together, there's one very nice property you should remember from abstract algebra. The inverse of a function is what? Inverse in the group is what? Unique. Inverse is always unique. If inverse as this, right? Inverse as this, it is always unique. No other people can do the job, same job. And another important proposition is a function f from S to T is invertible if and only if it is a bijection. Okay, this is quite a nice result here. Then you should prove it. So if it is invertible, then you should prove that. Why is it the bijection? Why is it surjective? Why is it 1-to-1? Okay, if it is 1-to-1 and onto, can you produce an inverse image or not? I claim that the inverse image is simply the inverse. Sorry, the inverse of the functions is simply by taking the inverse image. Because it's 1-to-1, 1-to, so you make sure that there's only one thing inside your image. Okay, so I use pre-image and inverse image. These two are the same word. Okay, by the way, same meaning. Okay, try and prove this. These are very good exercise to recall what you have learned before. Have you proved this at some point in your first year or second year? Invertible implies bijection. Yes or no? Yes. As assignment or what? I don't know. Yes. Yeah. Try and write it out. This is to make sure you know the definition. Okay. Next, some very pretty result. Okay, let's say we have two maps from S to T and T to U. I also use function and maps changeably, so they are the same thing. Okay, so if FG are injective, okay, then GF, okay, is injective as well. Similarly, if FG are surjective, okay, then GF is surjective as well. Okay, C. This one is quite useful. If GF is injective, can you say something about G of F or not? Okay. What we can do is we can say that the inner one, okay, F is injective as well. Okay. Outer one, never mind. But the inner one have to be injective. How about, let's say GF is surjective. Can we say something about G or F or not? We can. Okay, we have to make sure that G is surjective as well. Okay, maybe let's try prove two of them here. Let's see which one to prove. Let's prove the first one. Okay, so 1 and 2 have similar flavor. So let's do A. Okay. So want to show what? Want to show if FG injective, then GF injective. So your goal is GF injective. So to say that GF is injective means what? Suppose GF of where we start our S. Okay, S1 equals to GF of S2, and then we want to show that X1 equals to S2. Okay. All right. What do we know? What do we know? So we know that G is injective, right? Since G is injective, this means what? You see, you have G of something equals to G of something, but G is injective, meaning the thing inside have to be the same. So meaning what? Fx1 equals to Fs2 because they map to the same place. Okay. But again, F is injective. So S1 equals to S2. Okay, so similar flavor for surjective. Or I can find one back, I can find the other one back. Okay, yeah. So this is part A. Let's try C. Actually, this C very important, or this injectivity. If you side story. So this injectivity, right? If you still remember from abstract algebra, there's an injection map from group to term X. Where you look at the group action, right? If you have injective map from a group to term S, meaning you have a faithful action. But in research nowadays, we want to look for faithful group action so that we can study group using set elements. But it's really hard to find this injective map. So what we do, we keep composing. We keep compose until we find the injective map. And then we can conclude that the first one has to be injective. So we can bring the larger result to a result we want. Yeah, but this is just a side story. If you don't get it, that's okay. But what I want you to get out from here is this is very important. Okay. Yeah. But in future, if you get a chance to go into mathematics research, particular C and D, C and D, these are very important. Okay. And generate great result. Okay. So suppose let's proceed. So what we want to show? We want to show that F is injective. Okay, so what do we know? We know that GF is injective. Okay, so we want to show F is injective. So meaning what? Suppose again Fs1 equals to Fs2. We want to get what? We want to get S1 equals to S2. So this is the final goal. Okay, we want to get this. So how to use that GF is injective? So what can we do? We have Fx1 equal to Fs2. What can we do? We got a G composed on both sides, right? Okay, so consider GF S1 equals to GF S2. What else can we do? Yeah, what's injective now? Wait. What's injective? My question is GF is injective, right? So meaning what? So you see, you should see GF as a one function here. So GF is GS is injective. Since GF is injective, injective means what? GF x1 equals to GF s2 implies x1 equals to x2. And this is what we want to get. So you need to be very hold on to your definition very closely. Yeah. Then you will easily see what's going on. Okay. Yeah. So show B and D yourself. Same way. See this corollary follow where is it? Okay. So the corollary follow from this proposition will be if you have two bijection. Okay, if you have two bijection, then the composite are also bijective. So going the other way, GF is bijective. Okay. So since this is corollary, right? Corollary typically means it follows from previous result with almost no proof. You just apply. Okay. So you apply what? Just apply A and B. A and B. Just apply A and B, and you will get a result. Yeah, try and write it down. Whatever I say, right? Seemingly trivial, but make sure you know how to write it down. Okay. Please write everything down. If you are a person, I used to be this kind of person. It's like anything I don't know, I need to write down. Otherwise, I forgot. Otherwise, I don't know. So you have to write it down once, at least once, if you are this kind of person. Then the next time you can try to skip, depend on the level you're talking. Okay, but try and write everything explicitly down. Okay, if you are unsure of anything. Okay. All right. So what else? Yes. Okay. So come to our big subject now. Okay. So far, before we jump to the next subject, is everyone okay with this function, image, pre-image, range? Yeah.
How is G and how we can know that G is
Wait, which one? Which one?
the
Oh, you mean how to prove it? Have you tried? Sure. I mean,
because if it says the
Yeah.
G is surjective, but what if we don't know about F, right?
Sure.
And then how can you map all the things inside?
the claim is you don't need that, right? You don't need that. You see, GF is surjective, right? So there's something mapped by GF to something the domain. So is G surjective or not? You just pick F of that thing. And you try and write it down, try and think about it. And try and write down your problem. See your problem makes sense or not. And then why it makes sense, why it doesn't make sense. And then we can discuss again. Yeah. I think I somehow know your problem because when I first look at this, I also have some sort of vehicle, but I just ignore it because I know how to prove already. But you can try and write down your problem and then see whether that problem makes sense or not. And why does it make sense? Why it makes sense? It will be a great help for you to think about similar question in future. Okay. Yeah. I think you can find a counter example. You should be able to find a counter example. Try and find one. Try and find one. If can, then your sentence will be written here. We need to prove already. You know? So try and see if you can come up with a counter example. F not subjective, but GF still subjective, and then G subjective. Okay. Try come up with a counter example. If you come up, let me know. Okay, send me. Okay. We come to a last topic of the day, a big issue in maths, which is the axiom of choice. There are few variants of axiom of choice. In this class, maybe we at least discuss 3 of them, and then we attempt to prove them. Okay, we attempt to prove them. So first axiom of choice, I think this one is given by the monk Chris. He uses this. So given a collection A of disjoint, okay, disjoint, and then non-empty set. Okay? Disjoint non-empty set. So we are using whatever we introduced before. There exists a set consisting of exactly one element. There exists a set C consisting of exactly one element from each element of A. See, element of A, A is what? A is a collection of non-empty sets. So inside A here, you should imagine inside A here, there's a lot of sets, and then there's no intersection, no non-trivial intersection. Okay. And then there's another set, C. Okay, you should imagine C. C here, by membership, what is in C? Exactly one element from each set in A. Because element of A now is a set. Okay. Let's make it clearer. That is a set such that a set C such that C is a subset of the union of set in this A. Okay, with script A. So we write capital A for its element. Its element is a set, right? So keep in mind, these are sets. Non-empty set, disjoint non-empty set. Okay, so this is how you read it. Okay, so this is how you read it. later I share you how you read this sentence. And for every okay, I think I'm trying to be stupid here. Here is capital. For every A in A, okay, the set C intercept A is a singleton because you only pick one from them. Okay, a set with one element is called a singleton. Yeah. So you see, how I read this sentence, right? When you read sentence, it's like this: forward, 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 like this, right? Disjoint, non-empty, like this set. So which one is more important? Actually, the set is more important. Only come with this adjective. This is how you read the sentences. Okay, you cannot read at disjoint and then stop there, or you read until non-empty, stop there. There's no meaning. These two things have meaning when you have a set here. What kind of set you are interested in? Non-empty one, disjoint one. Okay, okay. So when you read English text or what, you need to take care of these what do we call nouns. Okay. For example, 蛋炒饭. Fun more important or 蛋 important? Both. Okay, good, very good, very good. I mean, it is true that both of them is very good, but which one is which one is the main dish? I mean, main object in your dish. So this is a view of a different culture. For example, we say 炒饭, we put fan at the back. But Malay put nasi in the front, nasi goreng. Nasi more important. More important one they put at the front. Which one? I don't know which one people see which one is more important, but you can see that for the same object, right? People will tend to put the order in a different way. So you should ask whether that culture, do you value nasi or you value goreng? I don't know, but you need to ask. I'm not Malay, right? Yeah. Even in the Japanese language, they also have an opposite order of sentence tenors. Right. There was mentioned about the object first, and then they say what to do with this object. But we say what to do and then with this object. Okay. Maybe we don't have time to prove, but I put up a lot of equivalent statement to hone you first, and then next week we'll prove it. Okay, make sure you learn this statement well, and then we will prove it. So actually, we can relax the statement in this axiom of choice. Really, we can actually throw away disjointers here. So I will give this lemma here. So given a collection B of a non-empty set, okay. So here we don't require it to be disjoint anymore. We still can find a function. Okay, we still can find a function. This B to the union of set inside my script B, such that I still can pick element from B. Okay, there's a lot of B here. Please be careful. So what this function do is I give you a set inside my script B. Okay, you give me an element that is inside that set B. Okay, so you should see that this is a generalized argument, generalized statement from the action of choice I give you just now. Here we relax the condition, not necessarily disjoint. Okay, but we can prove this lemma using the axiom of choice just now. Okay, so meaning if I want to use the statement just now, what do I need to do? I actually need to produce I need to produce disjoint subset out of this, possibly not disjoint. Okay. So this is my strategy to use axiom of choice. And there's last 3 minutes here. Okay, so this is a strategy of proof. This proof is in the book, and then I will show it to you next time. And then there are a few more. Okay. So those epsilon of choice are equivalent to 1, 2, 3, 4. Okay, this 4 statement here can be proven. I think we will try and do it in class as well. So what are these statements? So quickly run through it. So I call the first one axiom of choice 1. Okay, the one I write in white. The one I write it as a lemma is axiom of choice 2. Okay, and there's another axiom of choice 3 here. So for any non-empty set, okay, there exists a function from the power set of x to x again, such that f of an element in the power set give you an element back to that set A. Okay? For A, which is non-empty. 2, if f is a function with a domain A, okay, I don't care what's the codomain, there is a function f with the same domain, such that if you know that hash of some x in A is not empty, then what this f can do is f pick up an element in HS. Okay, you see pick up, pick up here hinting you how you're gonna use previous axiom of choice, because what we did before is we can pick something out. Okay, and then 3, if there's a relation, okay, there's a subset relation of the Cartesian product of A and B. There's a function from A to B such that it's a subset of this subset of A cross B. Okay, because just now we defined function as an ordered pair, so you can look at function as an ordered as a set. 4, actually 4 is the most important thing and most applicable in our course. So if G is onto map, okay, from B to A, then there exists a left or right inverse, okay, F from A to B, such that GF equals to identity. So this line here actually requires axiom of choice to make it, to define it. Okay, if you are given a subjectivity and then you want to find a right inverse, this have to involve axiom of choice. Okay, we will try and prove this. If you are there enough, you can try and go look for the proof first. And then I will try and motivate again this axiom of choice. Okay. Okay, see you hopefully next Monday. Yeah, next Monday. I will make an announcement. Come on.